Here's pre-calc. This is a closure problem. It's 6-147. And it says archaeologists use the radioactive decay of carbon-14 to estimate the age of an organic material. The half-life of carbon-14 is known to be 5,030 years. If a fossil is found to have 60% of the amount of carbon-14 compared to a living sample, how old is the fossil? So this one is a little bit different than the kinds of problems that we've done in the past. I'm going to show you a way that might feel more familiar to you after I'm done showing you the way that your book has it set up. So the way your book set it up is they just said, okay, so let's say that like A is 1. So whatever, 1 is going to stand for the whole amount of carbon-14. And this Y is going to be like, what percent of that whole thing is left? Or point, like this is, if there's 60% of 1, then that's 0.6. So 0.6 is going to be left. And then they're doing time over 5,730. And that's because every year, how can I say this? Well, maybe this is a better way to say it. If I were to plug in 5,730 years, wouldn't I end up with a half? And with half of the 1, and isn't that the half-life? So maybe it makes sense to say it that way. But after 1 year, 1 year is only 5,730th of a half-life, if that makes any sense. So each year is 5,730th of a half-life. So that's why the books is setting it up like this. And it's fine. It's actually much easier to solve. If you're going to do a half-life problem, you can just put how much is left over here on the Y, and then you can put the half as B as the multiplier, and then just set it up the way the book did. If you want to solve this, we're just going to use logarithms. Actually, they used, in the book, they used natural log, but natural log and regular, log base 10, they both follow the same rules. The reason you would want to log or natural log both sides of the equal sign is so you can get this exponent down. We want this, there's a power rule on our, here it is right here. There's a power rule, the power property. So this power property says if I have something up in an exponent like this, see how the Y is up here in the exponent, it can just come down out front and multiply when you're using logarithms. So that's why it's convenient for us to log both sides of an equation so that we can use this property, especially if the variable we're trying to get at is up in the exponent. So that's why we ln or natural logged both sides. And then I'm just showing that this came down out front. And then we're just going to solve for t. So I think I divided both sides by ln of a half. And then I also multiplied by 5,730 so I can get the t by itself. Then all I did is I plugged that into my calculator, and I got t is 4,022 years-ish. So, and I remember when we were talking about that, 0.6, we would expect exactly half of it to be left after 5,730 years, but this is there's a little bit more than half left. So we want the time to be a little bit less than 5,730. So that, I hope that made sense, but if that didn't make sense, this way you can see is a little bit longer, but this way is the way that I would have thought to do it. I always like to set up y equals a times b to the x just out of habit. So I would have probably started out with this assumption that if I start out with a whole amount, whatever the whole, we don't even know what the whole amount of carbon-14 is. Yes.
Dawn?
Yes.
Your family's here.
Okay, I'll come out.
Okay, thank you.
Okay, gosh. I'll make this really fast. So basically we are going to, I'm just going to have to start so I'll put a part B on this video, okay?